Good afternoon, students. In the previous class, we have discussed the structure of NH3 and NF3 molecule. Okay. Now today we shall study the structure of ClF3 and XeOF2 molecules. All right. The electronic configuration of chlorine atom. Okay. You can see here chlorine atom atomic number 17. All right. So in ClF3 molecule, Cl is considered as the central atom. So you need to write the electronic configuration. Okay. And what is the electronic configuration of chlorine atom? 1s2, 2s2, 2p6, 3s2, 3p2x, 3p2y, 3p1z. Okay. Now when chlorine trifluoride is formed, one electron from the paired 3p orbital, okay, you can see here 3p orbital, 3py orbital, it has got paired electrons, okay, paired 3p orbital get excited to 3d orbital, okay. You can see the box diagram here, 3s2 outer electronic configuration is 3s2, 3p2x, okay, and then 3p2y. So but 3p1y is there, one electron has gone into 3d orbital, okay. Therefore you have 3py1 and then 3pz1 and then 3d1, okay. So this is in the excited state, box diagram is given in the excited state, and this is the configuration in the ground state, alright, ground state. So when ClF3 is formed, one electron from the paired 3p orbital, that means 3py orbital, okay, gets excited to 3d orbital, alright. Therefore the new electronic configuration is like this, that means 3s2, 3p2x, 3p1y, 3p1z and then 3d1, alright. Therefore it undergoes sp3d hybridization, okay. S orbital, 3p orbitals and 1d orbital, all they combine, mix up to give rise to sp3 hybridized orbitals, okay. Therefore altogether there are 5 sp3d hybridized orbitals, alright. So we shall move to the next slide. These orbitals undergo sp3d hybridization, forming 5 orbitals of equal energy, okay. So 5 orbitals are present or mixing together or combining together, therefore you have 5 orbitals of equal energy, okay. These orbitals are arranged in trigonal bipyramidal shape, okay. And what is the shape of the molecule? Trigonal bipyramidal, alright. 2 orbitals containing a lone pair of electrons occupy equatorial position. You can see here 2 lone pairs are there, one lone pair here, another this side, okay, 2 lone pairs are present. They are present in equatorial position, okay, this is known as equatorial position. The 3 ClF bonds, okay, 3 chlorine fluorine sigma bonds, okay, are present, which are those 1, 2 and 3 down, okay. The expected bond angle is 90. 2 lone pairs here, this is the bond diagram, 2 lone pairs are here, one fluorine atom here, another down here, another this side, okay. So expected bond angle is 90, but the bond angle observed is 87.6 degree, okay, because of the steric hindrance of these lone pair of electrons. So 2 lone pairs are present, okay. Therefore because of steric hindrance they push the orbitals, okay, f orbitals, that is carbon and then chlorine and fluorine, okay, f orbitals, the orbitals of fluorine atom, okay. Therefore because of steric hindrance the bond angle decreases from 90 degrees to 87.6 degree, okay. Next slide. The bond angle decreases to 87.6 degree. The ClF3 has a slight bent T shape, okay. Therefore it has got slight bent T shape. Now let us see the other molecule, XeOF2. In that central atom is xenon, okay. What is the atomic number of xenon? 54, alright. And if you write the outer electronic configuration, you will get it as 5s2, okay, 5p2x, 5p2y and then 5p2z, and 5d is 0, okay. Now in the excited state, this is electronic configuration, 5s2, 5p2x and then 5p1y, 5p1z. That means from px orbital and py orbitals, electrons are excited to 5d orbitals, okay. These are the 5d orbitals, excited electrons. Therefore it undergoes sp³d hybridization. Okay, only till here sp³d hybridization, other one is unhybridized. There is one d orbital which is unhybridized, so undergoes sp³d hybridization. Therefore, altogether there are 5 sp³d hybridized orbitals. Okay, next slide. In XCF2 molecule, the central xenon atom undergoes sp³d hybridization. Orbitals are in a trigonal bipyramidal shape. Okay, since there is sp³d hybridization, shape is trigonal bipyramidal. Two of these orbitals contain lone pair of electrons. You know that two orbitals contain lone pair. Okay, therefore they occupy the equatorial position. The remaining 3 orbitals are half filled. So you have noticed that the remaining 3 orbitals are half filled. 2 of these present in axial position bond with the 2 fluorine atoms. Okay, 2 of these they bond with the 2 fluorine atoms in the axial positions. Okay, the third orbital is present in equatorial position, other one is present in equatorial position. It forms sigma bond with one half-filled orbital of oxygen atom. Oxygen has got half-filled orbital, right? Oxygen, what is the atomic number? 8. When you write the electronic configuration, you will find that it has got half-filled p orbital. So it will overlap axially, okay, forming what? Sigma bond. Okay, sigma bond. Next slide. The remaining half-filled p orbital of it has got 2 half-filled orbitals, p orbitals. The other one half-filled. The remaining half-filled p orbital oxygen overlap sideways with the unhybridized half-filled orbital of d orbital. You know that in the d orbital there is one unhybridized d orbital, correct? So the half-filled p orbital of oxygen atom, half-filled p orbital oxygen atom overlap sideways with the half-filled d orbital, which is unhybridized, okay, forming a pi bond. So a pi bond is also formed. That means in between xenon and oxygen there are 2 bonds. Okay, one is sigma bond, other one is pi bond. Alright, and the molecule has a T shape with the FXC bond angle of 89 degrees. The xenon oxygen bond length is shorter, okay, due to the presence of double bond. In between xenon and oxygen there is a double bond present, okay, therefore it is shorter. Double bond is always shorter than single bond. Okay, the shorter the bond, stronger is the bond. Alright, therefore it is a strong bond because it is shorter. Both ClF3 and XCOF2 have sp³d hybridization. Okay, the bond angle in ClF3 is 87.6 and bond angle in XCOF2 is 89 degrees. Alright, now in ClF3 there are 2 lone pairs and 1 bond pair at the equatorial position, and hence the bond angle decreases to 87.6 degree. Okay, whereas in XCOF2 the FXCO bond angle is much closer to 90 degree, that is 89 degree. Okay, 89 degrees is much closer to 90 degree. Now what is the reason? Because the repulsion exerted by 2 bond pairs of electrons of XCO is almost equivalent to the repulsion by the lone pair of electrons. Okay, since why the bond angle is very close to 90? Because the repulsion exerted by 2 bond pairs of XCO bond electrons is equivalent to the repulsion by 1 lone pair of electrons. Alright, next slide. The molecular orbital theory. So we shall move to molecular orbital theory. This theory was put forth by Hund and Mulliken in the year 1932. And what is the elementary account of the theory, or what are the postulates of molecular orbital theory? Okay, first postulate says that molecular orbitals are formed by the linear combination of atomic orbitals. Okay, how the molecular orbitals are formed? By the linear combination of what? Atomic orbitals. Okay, when the molecular orbitals are formed, the individual atomic orbitals lose their identity. Okay, now once the molecular orbitals are formed, the individual atomic orbitals lose their identity. Their identity will be lost. Okay, individual atomic orbitals lose their identity. Okay, now second postulates. What is the second postulate? The number of molecular orbitals formed is same as the number of atomic orbitals that combine. Okay, the total number of molecular orbitals formed, that is exactly equal to the total number of atomic orbitals that are combining. Suppose 2 atomic orbitals are combining, two molecular orbitals are formed. So, when two atoms combine, two molecular orbitals are formed. If three are combining, three are formed. Four are combining, four are formed. Okay, that's the meaning. Next slide. One is called, out of the two, suppose two molecular orbitals are formed. Okay. So, one is called bonding molecular orbital and the other one is called anti-bonding molecular orbital. Okay. So, bonding orbital and anti-bonding molecular orbital. Third postulate, a bonding molecular orbital has lower energy, okay, and anti-bonding molecular orbital has higher energy. So, when two orbitals are formed, the bonding molecular orbitals have always lower energy than anti-bonding molecular orbital. Fourth postulate, the electrons in the molecular orbitals move under the influence of two or more nuclei. Okay. How are the electrons moving under the influence under molecular orbitals? They are moving under the influence of two or more nuclei. Why? What is the reason? Because molecular orbitals are formed by the combination of atomic orbitals, right? When minimum two atomic orbitals are required, therefore, electrons in the molecular orbitals move in the influence of two or more nuclei, or in other words, the total number of atomic orbitals with which it combines. Correct. Next point, the necessary conditions, okay, for the formation of molecular orbitals is that the combining atomic orbitals overlap to a considerable extent and they have nearly same energy and have proper symmetry. Okay. The conditions for the combination of molecular orbitals, what is the condition? The combining atomic orbitals, okay, overlap to a considerable extent. They should overlap to a considerable extent and they have nearly same energy, and the combined atomic orbitals should have same energy, okay, and then they should have proper symmetry, then only they can combine to give rise to what? Molecular orbitals. Alright. Next slide. The rules for filling molecular orbitals are same as the rules for filling atomic orbitals. Okay. Now, the rules followed while filling the molecular orbitals are similar to the rules followed in while filling atomic orbitals. Okay. Then last postulate, seventh point, the shape of the molecular orbital formed depends upon the shapes of the atomic orbitals that combine together. Okay. So, shape of molecular orbital, or in other words, depends upon the shapes of the combining atomic orbitals. Alright. Now, let us move to the combination of atomic orbitals, linear combination of atomic orbitals. Okay. How is the molecular orbitals are formed by the linear combination of atomic orbitals? Now, first point, according to molecular orbital theory, MOT means molecular orbital theory, the molecular orbitals are formed by the linear combination of atomic orbitals. You know that molecular orbitals are formed by the linear combination of atomic orbitals, right? That is the first point. Second point, consider the formation of hydrogen molecule by the combination of two hydrogen atoms A and B. Okay, let us consider hydrogen molecule, which is the simplest molecule. Okay, how is hydrogen molecule is formed? By the combination of two hydrogen atoms. Okay, let us consider hydrogen atom A, hydrogen atom B. All right, and Xi A. Okay. Xi A and Xi B are the wave functions of atomic orbitals A and B. Let us assume that Xi A is the wave function of A, okay, hydrogen atom A, and Xi B with the wave function of hydrogen atom B. Alright, next slide. Linear combination atomic orbitals takes place in two ways. There are two ways of formation of linear combination: addition combination, or it is also called symmetric combination, okay, subtraction combination, or asymmetric combination. Alright. So, two types of combination, symmetric and asymmetric, or addition or subtraction. Okay. Now, first let us say addition combination. It is also called constructive overlapping. Okay. Addition combination is also called constructive overlapping. Alright. Atomic orbitals of same sign overlap with each other. Now, atomic orbitals, okay, Xi A and Xi B combine, addition combination Xi is equal to Xi A plus Xi B. Okay, let it be equation number 1. Alright. Next slide. Square of the wave function of an orbital gives the probability density of electron, which in turn is related to the electron charge density between the nuclei. Now, on squaring of the above equation we get, or equation 1 we get, xi squared is equal to xi a squared plus xi b squared plus 2 xi a xi b. Okay. Now, what does it indicate? That will indicate that probability density of the electron, okay, related to the electron charge density between the nuclei. So, when you say this, xi a squared, xi b squared and xi squared are the probability density of electrons in atomic orbital A, okay, atomic orbital B and the molecular orbital respectively. The equation indicates that xi squared is greater than xi a squared plus xi b squared alone, right? And what is the factor? How much it is greater? By a factor 2 xi a xi b, correct? Xi a squared is greater than xi a squared and xi b squared, only this much. How much, to what extent it is greater? 2 into xi a plus xi b, correct? Next point. The electron density between the nuclei in the newly formed molecular orbital is higher than the individual atomic orbital. This shows that electron density between the nuclei in the newly formed orbital is greater than individual atomic orbitals. Alright. This reduces the repulsion between the nuclei. This reduces the repulsion between the nuclei, okay, and favors the formation of chemical bond, because electron density is present in between the nuclei of the two nuclei in the molecular orbital. This reduces the repulsion between the nuclei, because nuclei will be having like charge. So, in between the nuclei you have electrons, correct? Therefore, repulsion will be less, okay, repulsion between nuclei will be less. So, this will lead to what, or this will favor what? Chemical bond, okay. So, bonding, that is nothing but bonding in molecular orbital, okay. The bonding molecular orbital has lower energy than the combining atomic orbital and is more stable. So, bonding molecular orbital has lower energy, okay, than the combining atomic orbitals and is more stable, alright. Now, next subtraction, another subtraction, that is we say it is also called destructive overlapping or combination by subtraction, combination of atomic orbitals by subtraction, alright. The atomic orbitals of opposite sign overlap each other. You know that atomic or opposite sign always overlap each other. Let xi star be the wave function of the new molecular orbital formed by subtraction combination, okay. When you write in mathematical way, mathematical form, how do you get? Xi star is equal to xi a minus xi b, okay. Squaring, on squaring you get xi star squared is equal to xi a squared plus xi b squared minus 2 xi a xi b, okay. Now, what does this indicate? This indicates that xi star squared is less than xi a squared plus xi b squared, okay. Is it right? So, it will be less. To what extent it is less? Xi a squared plus xi b squared, because it is minus 2 xi a xi b, correct. From this xi a squared plus xi b squared, you have to subtract xi a and xi b, correct. Therefore, xi star is less than xi a squared plus xi b squared by a factor. What factor? 2 into xi a into xi b, okay. Next slide. The electron density between the nuclei decreases and the repulsion between the nuclei increases. So, here in this case subtraction combination, electron density between the nuclei decreases and therefore repulsion between the nuclei increases. Why the repulsion between the nuclei increases? Because like charges, correct? Nuclei contain like charges, therefore repulsion increases. This does not favor formation of chemical bond, and this is not the favorable condition to form what? Chemical bond, okay. So, this is called antibonding molecular orbital, alright, antibonding molecular orbital. The linear combination of two atomic orbital results in the formation of two molecular orbitals, okay. So, which are the two molecular orbitals? Bonding molecular orbital and then antibonding molecular orbital, okay. Next slide. So, here is the distinction between bonding and antibonding molecular orbitals, alright. So, first is bonding molecular orbital, next is antibonding molecular orbitals, okay. So, let us see the distinction or differences between bonding and antibonding. First point. So, bonding molecular orbital is formed by the addition combination of atomic orbitals, correct. What about antibonding? Formed by the subtraction combination of atomic orbitals, okay. Second point, electron density between the nuclei is high, correct. This reduces repulsion between nuclei and favors the formation of chemical bond, okay. whereas the antibody molecular orbital electron density between nuclei is less. Okay, therefore repulsion between nuclei, okay, this will increase the repulsion between nuclei and hence does not favor formation of chemical bond. Has lower energy than the individual atomic orbitals from which it is formed and hence more stable. Okay, bonding orbitals always have got lower energy, therefore it is more stable, whereas antibonding molecular orbital always have higher energy than the individual atomic orbitals. Okay, therefore it is less stable. Then bonding molecular orbital may or may not have a node between the nuclei. Okay, this may have a node or may not have. Okay, whereas the antibonding molecular orbital always has the node between the nuclei. Okay, so these are the differences between bonding and antibonding molecular orbitals. Okay, now next, conditions for the formation of molecular orbitals. Now what are the conditions for the formation of molecular orbitals? The atomic orbitals that combine should have nearly same energy. Okay, so first condition is the combining atomic orbital should have same energy. Okay, second point, the atomic orbitals that combine should possess same symmetry about the molecular axis. So combined atomic orbitals should possess same symmetry about the molecular axis. Okay, then third point, the atomic orbitals that combine should overlap to a considerable extent. Okay, only when the atomic orbitals overlap to a considerable extent, then only combination is possible. Okay, combination is possible which results in molecular orbitals. Okay, so these are the three important conditions for the formation of molecular orbitals. Okay, so I will stop at this stage. Alright, so any doubts, please, okay, clarify with me. Okay, so thank you, and we shall meet in the next class.